In this video we are going to simulate a fluorescent OLED which is set up in such a way that it will be enhanced by triplet fusion. A diagram of the OLED is shown in the top right. We have in the middle in yellow an emission layer consisting of 98% host and 2% dopant, where the energy levels are chosen in such a way that the dopant does not act as a trap for electrons, but it does act as a trap for holes, which means the energy transport will be quicker for electrons than for holes. So most of our recombination should happen at the interface between the hole transport layer, which is at the same time an electron blocking layer, as you can see, and very little recombination should happen at the electron transport layer. In this simulation we don't model doped injection layers explicitly, rather we attach effective electrodes which have basically the energy levels of doped injection layers. As a consequence, we have a large gap in work function, so there will be an inbuilt voltage in this device which we have to compensate with an external field. In order to make this an efficient TTF OLED, we will have to set up a large singlet triplet gap for our emitter and also for our host. So we will see how this is done. To start the simulation, we now switch to the workflow client, and we start by dragging the LightForge icon here from the different venues in the workflow window and dropping it. By double clicking the icon, a tab occurs here on the right where we can edit the simulation parameters, the system setup, etc. Let's start by giving this workflow name. So we go to File, Save As, and we call it Model TTF OLED. We start defining the system in the General tab. This is device layout. It's going to be a stack. Automatic boundary conditions. This means it will be periodic in the direction perpendicular to the transport direction. We have two electrodes attached, and we need electrons, holes, and excitons. Now we go to the I/O tab. Since this is a purely parametric calculation, we don't need any inputs from Quantum Patch or other software modules, so we will uncheck this box. And we continue to the Materials tab, where we can define our four materials. The first material is defined here. So this will be our HTL. So we name it. Here we can choose how we want to input the material parameters. EAIP, sigma, and L, that is energy levels, the energy disorder, and the reorganization energy. We want to input all of those parametrically, so in this venue. If we would choose some of the other options, starting with a QP, this means this particular quantity would be read in from input files which are obtained from Quantum Patch. The excitonic properties will be read in from Exciton presets. We will not use any ab initio calculations in this tutorial. So we start by putting in the values for the ionization potential. For the HTL it's 5.5 and the EA of 1.0. So this is a rather small EA, because this HTL also acts as an electron blocking layer. We choose the energy disorder of 90 millielectron volts for all materials and a reorganization energy of 0.2 electron volts. And we choose an Exciton preset, fluorescent. Now we add another material, which we call the TTF host. Again, all transport input parameters will be chosen parametrically, and the excitonics will be determined by presets. Now we have to plug in the values for the electron affinity and the ionization potential, which are 6.0 and 2.0 respectively. And these are the values for the energy disorder and for the reorganization energy. Now, in order to get a large triplet gap, we have to define a new Exciton preset. So to do this, first we're going to check the box Show Exciton Presets. Now we see that here a few boxes appeared. At the top of the box you can see the name of the preset, fluorescent. Then next phosphorescent, doping and TRDF. These are the 4 default presets. But we're going to add another preset, which will appear at the bottom. It has by now the name of the first one, which is fluorescent, but we're going to give it a new name. We are going to call it high ST for singlet triplet gap fluorescent. We'll slightly increase the decay rate to 2 times 10 to the power of 8, and we will also navigate to singlet triplet gap and increase the singlet triplet gap to 1.1 electron volts. Now we go up again. We can hide the presets, and for the TTF host now we choose the preset high singlet triplet gap fluorescent. Now we will add another material. It appeared here. We call it Fluoro Emitter. And again we'll input the energy values for EA and IP. (90 millielectron volts disorder for electrons and holes, and 200 millielectron volts reorganization energy, and we have to choose the Exciton preset for this high singlet triplet gap. We add another material, which is the ETL, at the same time hole blocking layer. All the inputs gonna be parametric. Use the fluorescent Exciton preset and values of 6.2 and 2.2 for ionization potential and electron affinity. So with this we find all the materials that we need. We have the ETL, the fluorescent emitter, the TTF host and the HTL, and the TTF host and the fluorescent emitter both have a high singlet triplet gap. So we go to the device section. To set up the device we choose a morphology width of 20 nanometers, which is a cross section of the device. This is periodic in this direction. Thickness of the first layer is our transport layer is 10 nanometers. HTL is the material in the layer, so we add a second layer. You can see here is the first layer. The second layer is separated from the first layer by this small line. We choose a thickness of 18 nanometers. We add another material to the molecule species tab in this layer, so we have the molecule species. And within the individual layers, we see this box called molecule species here in the second layer, but also the first layer has this box. And we can add another material for the second layer. The first material is going to be the TTF host, and the second material the fluorescent emitter. And we choose a concentration of 0.98 for the host and 0.02 for the emitter. Morphology input is going to be automatic. Since we don't supply any input from other nanomesh tools, this means the morphology will be a simple cubic lattice with a lattice spacing of 1 nanometer. So we add another layer for the ETL. It's going to be 10 nanometers thick. So we just have to choose basically here ETL. And now we have to define our electrodes. The work function of the whole injection electrode we let at 5 eV, and the work function of the electrode on the ETL side we put to 2.7 electron volts. Since this is a parametric simulation, we have to choose coupling model parameterized. The first entry is the inverse wave function decay length. The second entry is the maximum electronic coupling, which is here 1 millielectron volt. We decrease the coupling a little bit by increasing the inverse wave function decay length to 0.5. This is just to have a slightly more efficient simulation, so that we simulate less charge hopping in the HTL and from the HTL and in the HTL and so on. The same options we choose for the electrode on the other side, so we slightly increase the inverse wave function decay length to 0.5, and with that we have defined our device. To connect the different molecules so that charge transfer is possible, we go to the topology tab and we set the number of maximum neighbors for each molecule. So for a given molecule, this is a number of nearest neighbors to which hopping rates are calculated. So if this number is too high, the hopping rates that are calculated will mostly be 0, of course, for the majority of these neighbors. So since we have a simple cubic lattice, we put a 26 here, which is basically the first coordination cube in a simple cubic lattice. As a transfer integral source, here we choose Miller-Abrams, which means we have a parametric transfer integrals, which we now have to define for all pairs of different molecule species. We see this block pair parameters here. So for the pairing of HTL and HTL, basically we have one block here. We can add a second block and define basically the pairing between HTL and TTF host. And we can define a third one, defining the pairing for HTL and fluorescent emitter. Another one, TTF host, TTF host. Another one, TTF host, fluorescent emitter. Another one, TTF host, ETL. Another one, fluorescent emitter, fluorescent emitter. Another one, fluorescent emitter, ETL. And last, ETL, ETL. Now for the individual pairs, we can change the parameters which define the transfer integrals. So again, this is the inverse wave function decay length and the maximum number of the transfer integral. These are typical values for the holes and for the electrons. We will leave them as they are, but for dextro energy transfer, the value is a little bit high, as it is now equal to the electron and hole transfer integrals. It should be like 1 or 2 orders of magnitude smaller, so we put it here to 0.0001 for all dexter transfer integrals for all pairs of molecules. So we are now finished connecting the different molecules, and we can go to the physics tab. Since this is a simulation with the Miller-Abraham rates on a cubic lattice, we will uncheck super exchange. This should always be unchecked if you use Miller-Abraham rates. The rate equations, we use here the setting automatic, which means it will automatically apply appropriate rate equation for different processes. With this we are finished with the physics tab, and we can go to the operations tab. Simulations, we set to 15. That means for every data point, for example for a given applied field, we will do simulations in 15 different disorder configurations and average over the results. Temperature we leave at 300 Kelvin. DC, that means we have a normal DC measurement, and now we have to fill in the fields that which we want to simulate. In order to figure out what we should put in here, we have to consider the work function difference of the electrodes to compensate for the inbuilt voltage. As these are not real electrodes, but effective electrodes, as we said earlier, because we just replace doped injection layers with these electrodes as an approximation. So since we have one electrode with a 5 eV work function, the other one with 2.7, and we have a device thickness of 10 nanometers plus 10 for the transport layers, 18 for the emission layer, and a distance of 0.1 nanometer each between electrode and transport layers. We have a total field of 0.058 volt per nanometer due to the inbuilt voltage of the system due to the difference in work functions. So to get a current, on top of this we add 4 different fields. The smallest field will be 0.021 volt per meter, then 0.022 volt per meter, 0.032 volt per meter, and 0.042 volt per meters. So we can calculate the final fields which we want to apply, which are 0.07, 0.08, and 0.09, 0.11 volt per nanometer. 07, 08. Since we have no electrodes attached, we set both initial electrons and initial holes to 0. And now finally we have to set up the termination condition for the simulation. So we can set a maximum number of iterations to 600,000 for different kind of OLEDs which are less efficient due to higher barriers between layers or deeper traps. More simulation steps will be needed, for example by a factor of 10 more, 6 million or 20 million. This depends strongly on the device setup. The simulation would terminate early if a certain kind of stability criterion for the fluctuation of the current voltage characteristics would be reached. Since we do not want this, in this case we just put this criterion very low. This is so-called IV fluctuation. And the simulation would also terminate if we reach the simulation time of 100,000 seconds. Last, we go to the Analysis tab. Here we check this node and we check this box. We want to analyze Exciton life cycles, which will give us detailed information about how quenching occurs. And this item called autorun start we set to 0.1. This means that the tracking for the analysis of the system will start after 10% of the simulation time. So if you have a system that reaches steady state not that quickly, this number should be higher, for example 0.5, which would mean 50% after the simulation time the tracking for the analysis starts. One of the results from the simulation will also be a plot which will show you basically the cumulative particle trajectory over time. So from this you can deduce when your steady state was reached. So if you see your steady state was reached much later than this autorun start happened, your analysis which were done are not necessarily in steady state. So now we have finished setting up the device simulation. Now we have to set up our resources, the computational resources we want to allocate. To do this, we go first to the Operation tab, because we want to calculate how much CPUs we would to have ideally. So we have 15 simulations per data point, 4 different fields. That means 60 independent calculations. So we would like to have at least 61 computational cores, one to manage all the calculations and 60 so that all the calculation can run in parallel. So we go to the Resources tab and we put a CPU per node 61 if we have nodes which have 61 or more cores, and one node. We could also put to 31 here and 2 nodes. For the memory we put here 64 gigabytes for the entire simulation. Now we save the workflow and we submit it by pressing Run. Once the calculation is finished, we can inspect the results by navigating to the Jobs and Workflow tab. I double click on Workflows and we see that the workflow model TTF OLED is finished, so I double click it and I double click this icon, and here I could access all files. If I want to download a compilation of all the analysis, I could download results.zip by double clicking it and saving it somewhere. I can, however, also inspect the results using the browser in the workflow client. To do this, I do a right click on this LightForge 2 icon and I click on Browse Directory. Now a file browser opens and I will navigate to the folder Results. I will go on Material, Energy Levels, and here I see a cross-section of the energy levels over the device for the 4 different applied fields. So I click on the first one and we see our energy levels. To go back, I right click in the white of the screen and press then on back. Now I go back again until I arrive to this folder which has the experiments and material folder, and I go on experiments, then current characteristics, and first of all I'm gonna check the convergence of the simulation by navigating down here to until I find the file trajexall.png, and I left click it. What we see here on the x-axis is the cumulative charge displacement in units of the device length, and on the y-axis the progress time for the 4 different fields and for 15 simulations per field. So we see all of these are straight lines, which means the calculation is nicely converged. They don't have to be straight lines. It's also okay if they are wiggly. You should just be able to do a linear regression through them, otherwise you cannot say that you're in a steady state. Now I go back, I go up, and I click on iv.png, and here we see the current voltage characteristic. On the y-axis in ampere per square meter, so that's a factor 10 more than milliampere per square centimeter. I go back, and now I click on iqe.png, where I can inspect the internal quantum efficiency. And we can see here we have a quantum efficiency of around 20% for the smaller fields, and it drops off at the larger fields, the larger currents. So an internal quantum efficiency of around 20% would correspond to an external quantum efficiency of around 7% if you assume an outcoupling efficiency of like 30%. I go back, and I go back again to go out of this folder. And now I go to particle densities, and I navigate to the file quenching density average. So we have 4 listings here, 0, 1, 2 and 3. These correspond to the 4 different fields. Now I'll look at the quenching density for the smallest field, and we see in the bottom the charge densities for holes in red and electrons in blue, and at the top in black we can see where quenching occurs, that is exciton quenching. We will also look at this plot for a stronger field, for higher currents, and we see a similar behavior. Most of the quenching occurs at the interface to the HTL, where most of the excitons should be created, and where we also have a high hole density. If you look at the unit for the average number here of holes in this area for 20 by 20 nanometer cross section, with which was the device dimension we chose, we have a 1.2. Now going back to the smallest field, 0 here, we have 0.1, so it's less than 10% of charges at the interface for the weaker field. Now we will look at the files called Exciton Decay Density Average 3. 3 is here again stands for the third field, and then we can choose between different molecular species. Total means the summing of quenching events happening on all molecular species. And we see here on the x-axis again the device cross-section, and on the y-axis different kind of excitonic events. So we see all recombination in blue here basically happens at the interface between HTL and emission layer, and then we would need to zoom in to see these other events. Now I go back, a detailed analysis of the life cycles of an exciton we can find in the files exciton lifecycle.html. Now I'll open this for the second largest field here. I have to make the screen a little bit bigger. This pie chart shows the states through which all excitons go through. So to read it off, you start in the middle, which will be the creation event for excitons. Here we have two different creation events: recombination to a triplet for roughly 72% of excitons, and recombination to a singlet. And this small part of the pie is that is excitons which already existed when we started to track excitons for analysis. So this was after 10% of the simulation. So we have here triplets and here singlets. And you can also read from these boxes which appear on the top if you hover your mouse over this part of the pie on which molecule this appears. So you have the live mole type. That means on which of the mole type refers to the different molecular species. We have 1,469 events on mole type 1, so the mole type 1, that is material, was the second material which we defined, because we start counting with 0. So this was the TTF host. So almost all of the triplets here recombine on the TTF host. Life state refers to the spin state. 4 means a triplet and 3 means a singlet here. So all of these triplets are triplets. Now what happens further to these triplets? Here, this blue chunk, this blue part of them, blue percentage, is destroyed in a TTF process, so they are called TTF donor. Corresponding, the TTF acceptor is on this side, it's just called TTF. So these become converted to singlets, so their life cycle continues further. In green, you see 7%, they undergo radiative decay. In pink here now, that's singlet triplet annihilation, and there's a range of other processes that can happen. In such a way you can just basically analyze what the excitons go through in the life cycle, whether your TTF works efficient, for example, or your hyperfluorescence, and these kinds of questions. When the plot ends, like here, after the orange part, that means the exciton was destroyed. So here, move charge, that means they had an interaction with the polaron and the exciton just got destroyed. And tracking means the exciton was still alive at the end of the simulation, so we don't know what would have happened afterwards. If you look at the singlets here, what happened to the singlet next? So a big part of them was quenched due to singlet triplet annihilation, and also a big part underwent radiative decay. So if we add up basically all the green boxes here, we get the total radiative decay percentage, and we can clearly see that triplet fusion here is brings more than half of all the radiative decays due to triplet fusion in this device for this given field. So now if we go back and we look at the equivalent plot at the smallest field, which would be exciton life cycle 0 HTML, we see a very different picture. In brown again, these are the excitons that are created as triplet, but most of them actually undergo a thermal decay here because we have a very low exciton density at this small voltage, so there are no other triplets to undergo triplet fusion. Some of them are quenched due to interaction with the polaron, and here only a much smaller part undergo triplet fusion than before. If you look at the singlet, here the orange box is radiative decay, so we see that almost the majority of the radiative decay happens actually from the singlet excitons, as opposed to the stronger field, where the more than 50% due to the radiative decay was due to excitons which were created by triple fusion. Now we go back. So you can see that with this kind of analysis you get a detailed picture of what is actually happening in your device at different operation conditions. So this can be quite useful to find out bottlenecks in your device. With this, I'd like to conclude the inspection of the analysis of this system. If you want to know about a few more analysis that LightForge does, you can watch the webinar for the phosphorescent OLED, where I explain a few other analysis plots. Thank you for watching.